Turn it over to Alice. Turn it over to Alessandro for lecture 4 in this series.
Hello, everyone. Welcome back to the series. Um, okay, today I'll try to catch up from when I finished last time, but I guess a little bit of a recap is needed. So maybe I can just go back to the last slides and show them a little bit. So we have this map that sends paths like this. So m times n plus km to paths of size n plus k times n plus k with k decorated false. And we showed 2 lectures ago that using the argument by Gillespie, Gorski, and Griffin, that we can restrict to some very special labelings of these guys, in which we have all the labels from 1 to k in each column, except one set of labels from 1 to k is missing, and the way, like, if you draw the complements like we do here, then they appear in increasing order while getting further from the diagonal. So it's more convenient to switch to this representation here, which what we do is in each column after the vertical steps, we go down by k each time. And then we sort of label the missing steps here, like the down steps that are not paired with anything, with the complement of what's the red labels in the column. And the way our map works in this context is just deleting the pairs of like red labels followed by orange steps, south steps. So we get an object like this. And all that's left to do is to show that the dim of this gadget here is the same as the dim of this gadget here. And the trick is that I didn't say what the dim on this gadget here is, so I can just pretend like that's what I always intended from the beginning. So we managed to split the dim here and the dim here in a few parts. A part is like the temporary dim, like the attack relations between these small labels, which are depicted in blue. And then here we have a correction that depends on the shape. And here we have, well, I mean, we have a correction that depends on the shape, but we also have all the attack relations between like big labels and themselves or big labels and small labels. So all in all, here we have a bunch of terms that are this temporary dim here, just like the attack relations between any kind of label. And then the correction is minus the number of occurrences of this pattern here. And then if we also consider paths that go below them in diagonal, possibly, then we also have another correction, which is the number of steps starting below them in diagonal. Just 1 plus 1 for each step. So all in all, we have for the left-hand side, we have all these terms. This one here is counting attack relations between big and small labels. This one here, no, sorry, apologies. This one here is counting patterns like this, where this label is small. And CB is the same when the labels are big. So is like the dim correction, and this shows up with a minus sign. Then we have this, what we long ago called bonus dim, which is plus 1 for each label below them in diagonal. And here we split it into small labels and big labels, because why not? And then for the actual temporary info, so for the attack relations between labels, we have this, which is pairs ij, where I is small, j is big, and I is to the right of j. Here we have the same, but they're both big, and the smallest of the two is to the right. And then we have a third term that counts both type inversions, but in which the smallest of the two labels is on the left, regardless if it's big or small. So the one on the left is smaller, but they might be both big, and in this case, the one on the right is bigger. And then, of course, we have one extra term, which is attack relations between the small labels and themselves, but we don't count it at all because it's going to appear exactly the same way, like the exact same term where it's going to show up on the right-hand side, so we might as well ignore it. So this is all the stuff that we have on the left. And on the right, we have pretty much the same. Well, we have the temporary div, and then we have the corrections, but the corrections now we have three types. So on the left, we only have this thing that shows up with a negative sign. On the right, we have three different terms. This one, that's sort of correction involving the decorations, which is stuff like this, which shows up with a positive sign. Then we have exactly the same terms before, which is the same correction as in the other case and shows up with a negative sign. And then we have this kind of patterns. So vertical steps that project onto long horizontal steps that show up with a plus sign. And this correction, like technically it's still there on the left-hand side, but it never happens because we have no decorations. And so like the projection gets longer than 1 unit because the path is taller than wider. So that never happens. I think I'm messing something up here. Yeah, it's probably the other way around. Anyway. So the point is one of the two, like they're both there also for non-decorated paths, but when the path is not decorated, we can only have one of the two, depending if the path is tall or it's wide. And in our case, since the height is always greater than the width, then we are only getting this term here. Now I'm a bit confused by this picture, but that's what was there last time. So maybe let me just double check. Um, yeah, right. Indeed, I got it the other way around. This shows up with a plus sign, and this is what happened in the previous case. But in that case, the path was very tall, so this could happen. And this could not happen because if the path is tall, when I project this thing, the length, well, when I project this thing, the length is greater than 1, and I don't get I can't fall inside a single step. So now should be correct. Maybe I should edit the notes from last time. So on the things, we want to show that the div of pi tilde is the same as the div of pi, where pi tilde is the starting tall path, and pi is the ending decorated path. Right. So what is this? Div of pi tilde And the temporary uh, contributed by the small labels of pi tilde, which is the term that we're gonna delete later. Then we have we have a bunch of cardinalities here. We have start with a minus the patterns as above, depending on whether the label is big or small, plus the number of things below them in diagonal, regardless if they're big or small, plus the attack relations that I mentioned before. Well, yeah, there are cardinalities everywhere. And we're gonna recap what each set is while we discuss it, but now let me just write them out. And the rim of pi is, well, the same thing. And these two terms are the same. And then we have minus what we call C minus plus, yeah, I guess I should add some cardinalities here, where these are the corrections, well, of the three kinds. So the ones involving decorations, the ones, well, I might as well. C star is this, C plus is this, C minus is this. Number of patterns like that. And that's it. That's all there is. So what we want to show is that all of this is the same of all of this. And that should complete the proof once we actually manage to show this identity. Oh, yeah, no, sorry. There is one extra term, which is the number of things below them in diagonal. But now, this is the same as this, as we said, and this is the same as this, if you think about it, because how many things do we have at the end of the process below them in diagonal? Well, the ones that survives are the small things that we had before below them in diagonal. The distances don't change. The big things are disappearing when we do the psi map. The small things are there, so these two numbers are actually the same. So we can ignore them as well. And now we want to show a bunch of things. Okay. We have one statement that we're gonna prove later, which is that the cardinality of C plus minus the cardinality of C minus is the same as the cardinality of Fs down arrow minus the cardinality of C tilde small to show. And then what's left after this simplification, let me highlight this in pink. This and this. So what's left is to show that minus tilde b plus b tilde b plus this plus this is the same as this. And it is slightly more convenient to rewrite this as cardinality of C star plus cardinality of C tilde B minus cardinality of FB down arrow minus cardinality of F up arrow equals B tilde B. Okay. And we'll see in minutes, hopefully, why this is more convenient. So let's start with the latter. So with this identity. And what we want to show is that this is what we mentioned last time, that the expression in parentheses here yeah, it was very annoying to write all these things even when actually writing the paper. So yeah, that's part of the experience. Counts the intersections between half lines Li with steps in horizontal union down not decorated, union down decorated, belonging to pi I pi wi, I guess. What do I call it? This meaning that the uh, uh, labels of those steps are less than the label of step I. These things summed over I. So what we do is for each I in big steps. So for each vertical step with a big label, we draw this half line. Let me go back again to some picture from last time. Yeah, here. Oop. So we take this horizontal step here, we take the starting point, we draw this line, and we count the intersections with horizontal or down steps uh, which show up in the path in which we delete all the labels that are greater than that one. So for example, this one has no relevant intersection because it does intersect these two south steps, but the matching north step has the same label and we want one smaller one. I'm not even sure there is an example of some, yeah, I guess this one here crosses this one here, which is fine because its label is smaller, probably crosses this one as well, which is fine because it's horizontal. So these are the things we want to count. And the idea is reduce to this to count in pairs ij with I same as before. J is now horizontal. J less than I, so it has to appear on the left, obviously, satisfying certain constraints. more low level, the idea is that if our line intersects some south step, then we can uniquely associate this south step to some horizontal step, which is the one immediately after. Well, there might be more south steps below, but it is that we are counting intersections like this. So the line with something that if it goes down or like goes down all the way and then goes east one. So these kind of L shapes. And intersecting such L shape, I mean, obviously you can intersect it only once. You cannot intersect the same shape in multiple places. And then we want to write the condition of intersecting the shape in terms of some inequalities. And then we see that like the inequalities are the same inequalities that are satisfied by some other term in the sum, and so they will cancel out. That's pretty much the idea. So for I, J such pair, we let R prime IJ the number of decorated steps before J with label less than WI. So pretty much the length of this down thing, well, not really. The length of this thing, because we count decorated steps. The decorated ones are the ones that don't match um sorry, don't match some label that's already in there. And actually here it's greater than WI. Why this? Because remember the labels associated to those steps, I didn't draw them, but maybe again I should. They're the complement of the label appearing in the term here. So the south steps are sort of labeled, but they're labeled like in a predetermined way. So there is something to like consider, but I mean they're not influencing the cardinality of our set. So we have some virtual labels, but the way we assign them is fixed. So yeah, we can pretend they're not there, but we are looking at this condition. So the condition is pretty much that in the column um, we're missing some stuff that it's at most I like WI. Okay. We don't care about things that are greater than um, smaller than that. And another thing that we should recall, well, is that in these decorated steps, each label appears exactly once. So there is at most, well, there's exactly one decorated step label WI. Okay. Um, we call that, we call that I star if that label, that step shows up among these. Okay. So what's the distance from of this I star from the diagonal? I yeah, the vertical distance. Well, it's the same as the vertical distance of, well, maybe I should copy the picture so at least we can see something. That is pretty much a terrible example. Maybe I should draw a new example that works a little better. Um, yeah, doesn't really matter. Let me finish this. I'll write this down and then we'll see why that holds. So we have this I star somewhere before this step J. So we're counting. Okay, let's go back to this example. We have, no, the diagonal I wanted to keep. We have this 3 here. We are crossing this guy here. And we want sort of to pair this guy here. Maybe I should draw the 2. Maybe it's a bit better. Yes. Let me use this step instead. Okay. So this half line is crossing somewhere here, probably here. So we're pairing this step with this horizontal step. It's the horizontal step immediately after. So in this picture, this is I, this is J, and this is I star, because it's the unique south step that's labeled with the same label as I. I hope this is a bit better now that we have a drawing and we can follow the argument a little bit. So what's the vertical distance from this guy to the diagonal? Well, it's this distance plus the slope, because we go down, um, follow this step. So we get the slope, which is n over m. Then we get the number of decorated steps before j with label greater than wi. In this case, it's 1, because we have to go up like all the way. So plus r prime ij. Um, and then we'll try to convince ourselves that this is true. Yeah, sorry. Y minus 1. I'm a bit confused by this minus 1 here. We start from this, we go up by the slope, we go up by r prime ij. And then why do we go down by 1? Uh, we'll figure that out later, but let's believe me for a moment. this should be the formula. At least that's what we wrote on the paper, so I hope it's correct. And then we let our second ij to be 1 if I star exists and 0 otherwise. So, okay, in this case, I star is defined because, well, in this, I mean, if I star is among the steps that precede step j, that's pretty much what this means. So in this case, so if we take this intersection with this horizontal step here, this, and if I call this, say, j prime, then our second I j prime would be 0 because the south step labeled 2 is not among those preceding this step here. So it's basically, it's 1 if 2 star is somewhere before j, and if 0 is 0 otherwise. So now let's count these things for fixed I. So for each such intersection, we can consider the corresponding j, so the corresponding horizontal step below the intersection, or maybe it is the intersection, that's also fine. So what's the inequality that holds if we have such an intersection? So if I here intersects this thing, we have that Vj is less or equal than Vi. And it should be less than what? The height of the top thing here, whose label is at most Wi. So in this case, it's full. In this case, we stop here because this label here is the same as this, and we should stop before. So here we count this length. Here we count just this length here. So what's this height? It's, well, it's Vj plus the slope again, plus r prime ij, so the number of decorated things, plus what? Plus the number of labels here that are smaller than this. But of these, we have exactly, by definition, we have Wi minus 1, right? Because all of these are, I mean, the ones that we're counting here are the ones that are greater than 2. So in this case, it's 0. In this case, it's 1. And then we have to sum all the labels that are smaller than 2, because either they're decorated, but so they show up, or they're not, and well, they show up before 2 in the vertical line. Does that make sense? So of those steps, we have exactly this number. And so this is the condition. I mean, there's a little abuser notation because Wi is barred, but whatever. Okay. And so we want to, like, this is the inequality counting the intersections of this kind. And now we want to count these things. So this thing here is a condition to have an intersection. Okay. So let's look at these three terms. Let's start with this FB down arrow. And let's go back to the definition. So let's, I mean, this is the cardinality of this guy. And what's the attack relation? The attack relation is VI, I attacks J, so it should be VI less or equal than VJ, less or equal, am I getting this right? No, sorry, VJ less or equal than VI. Okay. I attacks J, I is the one in the middle, I think. VI less or equal than V less, strictly less than BJ plus 1, I think. That's just the condition. Double check just to make sure, but no, it's okay. It's completely wrong. It was I before. So, okay. Okay. So okay, this is bad, but what we want to say is that for what we want to say is that for I in B and J in H with J less than I, there exists a unique I prime such that I prime belongs to this set here, and with I prime here um, above J. I mean, in the string above J, this, if and only if we have a given inequality. So when do we have such a thing? So let's go back to our picture. We have our, do I have a decent example here? I think this probably fine. These three here intersect these two. So this would be an attack relation. And it's involving this step here. So we should consider the condition with respect to this horizontal step. And the condition is that, okay, we want to plug in I prime I think I'm confusing something because I kind of wanted the other one to be in the middle, but we'll see in a second. Maybe let's make a picture. Right. So we have some step. Let's say it's labeled bread 4. And we have some line. And this is crossing something. And we have some step J here. We have some labels here, say 1, 3, and then maybe 2 or 5. I guess these are the start ones because they're, I mean, these steps are going down, obviously. I got the wrong picture, obviously. Doesn't matter. Okay, so a little bit like this. Okay, so what's happening? We have a bunch of labels. We have the complement here. We have this intersection, and we want an attack relation. That means that this is a bad picture. It means because when do we have an attack relation? We want an attack relation in which the small label is to the right, because that's what this set is counting. So we want something like this, probably, maybe a little higher as well. Let's do the other way around. Something like this. Right? This is the condition. This is the condition for this to be an attack relation. We want the endpoint here to be less than this. We want the big one to be in between the small one here and the big one here. That's what's written here. So that's fine. All right. So we're saying that this exists. This happens. If this happens, what's the condition on J? Like what inequality do we have between this height here and this height here? Well, this height here, because we want sort of this, well, whatever, doesn't matter. We want this to be, so what's this height? Let me give names to these things. So this is A, this is B, this is C, and we want A less or equal than B, less than C. So what's A? A is Vj plus the slope plus the number of decorated things here, which is R prime ij, plus the number of labels here that are less than this, which, as we said before, is just wi minus 1. Well, sorry. The decorated things here that are greater than 4, this is this. And then wi minus 1 is this. Plus possibly 1 if the thing labeled 4 star is in here, because then we are not counting it in R prime and we're not counting it in wi. So if it shows up in this column, we should add 1. And if not, we don't. This should be less or equal. Should move all the picture. Maybe we're not finishing today, we'll see. Less or equal than vi, I prime, I guess, which is this number here. No, vi, sorry. Vi is this. Well, vi is this, but b is dot plus 1, whatever, so we can get rid of the 1. And then this is the same thing plus 1. Well, not really. This thing is anything that's above here. So it's the same expression, bj plus n over m. But now we want to go all the way up along the column, and the column has length k by construction. All the columns have length k. So then when we shift down by 1, because that's what we're doing everywhere, we get k minus 1. This was probably a bit confusing. So in this case, this height is our prime ij, so the things bigger than 4 here. Then we might or might not have our second ij if we have decorated 4 in here. And then we have wi. Well, wi in this case is all this. I guess I should add, what I'm really doing is adding 1 everywhere and then getting rid of the 1. It's a bit better this way, but imagine I'm adding 1 everywhere, so that's wi. And so this thing should cross something like this, and then it should end above, like before the end of the column, like the end of the whole decreasing thing, which is exactly k by construction. This thing has height k regardless of what the path does. After you stop going up, you have to go down by exactly k. That's how the map works. So we have one contribution to FB star if and only if this happens for given I and j, the horizontal step. And of course, for each column, you may have at most one contribution to B star because, well, you can cross at most one step with this line, and that's the condition for giving an attack relation. Well, good so far. This was a bit more painful than I expected, but I hope it's fine. If it's not, please tell me. Okay, no one is complaining out loud. Maybe you're complaining internally, but that's okay. That's fine by me. Okay, so we got rid of one of the 3 terms. Let's go to C star. Now fix ij such that I star is defined. So our second ij is 1. And we want to count contributions to C star from pairs I star j prime, where I star is what it is, and j prime is greater than I and has at least one endpoint below I. Right. So what is this thing? This is a terrible picture, but whatever. Let's draw a picture to see what's going on. We have some labels going up. Then we have our steps going down. Have some labels. Say again, we have 1, 3, 4, 6, and then here we have 2 star, 5 star. Here we have our J. And then somewhere we have our step I, our step J prime. And here is, say, this is the name of the step. I should put the label. Okay, this is a 2. This is something we don't care. Well, we care a little bit, but okay. So in this case, so this is I, this is J. So I star is defined because the 2 star is above J. That's this condition. We have some line here. That's a contribution to C star by definition of C star. And so what's the condition here? So notice that in between these two, we have exactly Wi minus 1 things. Because if we have a label in between these, well, I mean, we know that it's exactly 1 actually. So let me put this down, 1. We have 2 cases. Either it's a red 1, because if it's red, it's going to be smaller than 2. Or it's a blue 1, because, well, if it's blue, it's also going down that way. So doesn't matter. This is exactly Wi minus 1, this difference here. This is J prime. This is I star. So what's the condition for this line to be crossing this step? Right, this is gonna be painful. So the condition here tells us that Vi is, well, what we call Vj plus. This is not a plus. Vj prime plus. Why is this? So it's the height here. Plus Wi minus 1 by definition. So this is the height here. This is Vi, this is Vj. So we have to go up here. Why it's not just 1? And up here. That's probably just 1. Whatever. So J prime is determined by this condition. And this thing contributes to C star if and only if Vi star, I mean, this has to be below Vj plus prime. So this point is below this point, and this point is below this point. Vi star plus 1. So now we replace this quantity here, well, the right quantity. And so okay, and also let's recall what Vi star is in terms of Vj. So Vi star is Vj plus the slope plus R prime Ij. I think that's it. So it's start from here, go up by the slope, go up by the number of decorated labels less than this one. So let's replace all these things in this formula. We get Vj plus n over m plus r prime ij less or equal than Vi minus Wi plus 1 strictly less than Vj plus n over m plus Rj r prime ij plus 1. And now we can move things a little bit. And this is the same as Vj plus n over m plus r prime ij plus wi minus 1 less or equal vi, strictly less. I can do it. Vj plus n over m plus r prime ij plus wi. That's probably it. Yes. I do have a -1 floating in my thing. I don't know exactly why. Okay. Oh, and actually, well, hold on. What's written in the paper, and then we'll figure out what's going on. Is oh yeah, yeah, okay, I get it. I get it. Okay. Well, give me a second. So we want to rephrase this a little bit. I mean, we're considering the steps in which I star is defined. So if we um, consider everything, actually, we can plug in a minus r second ij here and get rid of -1 here. And then, okay, I don't know exactly why this is happening, but um, bear with me for a moment. So if we ignore every restriction, we should get something like this for this condition here. And this, well, is never true if this is 0, because if I get rid of this thing, then this is the same as this. And we have a strict inequalities and nothing happens. But if this is 1, then it is saying something, and we are in exactly in the case in which I star exists. So we can only count the things in which this I star is defined, which are the things like this. And so these are the contribution to C star. So if I write this condition of intersecting like naively, I should get this. So this never holds unless this is 1. And if this is 1, we should get this condition here. And I still don't understand why there is this -1 floating around, but um, I don't know. Anyway, so I can, well, whatever, it's fine. Um, okay, it's already 7, and this is definitely not done, but I'm also very worried that everything is gonna be a mess. Also last time. I mean, if that's of any consolation, this happened all the time when we were writing the paper, and like every time we did some computation, it was one off something, and we had to do it so many times until we got them right. But yeah, there is some off by 1 somewhere. I'll try to quickly finish what I'm saying, and then I guess we will need another lecture. So the idea is we want to the condition to have an intersection is this one. We want to split this inequality in a bunch of different inequalities so that they encompass the intervals here. So these two will get a larger interval, and the missing part is going to be this one. So here we have this Vj less than Vi less than this thing. And here the part for B star is something like this, which is Vi less than something that really looks like this, less or equal than this, less than something else. So in the end, the positive contributions, because this FB moves to the right hand side of the inequality, we're gonna have when Vi is between Vj and this number here. And then when we count the contributions from C star and this C tilde B, we're gonna have globally the same inequality. This is the first half of it. And then when we take the sum, we will have a K appearing here because we have to sum over I and stuff will happen. And then the other term will correct the thing on the other side of the inequality. So in the end, the condition is gonna be Vi is in between those two, but the idea is that you split all the things in a bunch of different intervals, and you might fall in different intervals, but in the end, like you fall in the same large interval. So the number of things is the same. This was a bit hand wavy, and also the computations were not great, but we are already over time, so I guess I'll stop here.
All right. Thanks, Alessandro. Yes. Any questions before we stop for today? No? Okay, so we'll look forward to Thursday then, seeing the
Yeah,
completion.
we're
Yeah.
gonna have another very fun session of computations that don't adapt. I'm sorry, this is the proof. I can't help.
Well, we people outside combinatorics would really hate this kind of thing, but most of us like it, right?
Awesome.
Okay. So yeah, we'll see you all on Thursday.
See ya.
Bye.